Hello, Physics 2 people. In this video, I want to clean up some details that I just haven't quite pinned down, I think, well enough for us in class. So I want to go over electric potential, EMF, voltage, and all that. Touches on things that we've seen throughout the semester, but hopefully I can kind of state things in a clean way to dispel any confusions. I think in talking to some of you guys, it's been a little bit muddied. So thus far, we've been talking about electrostatics. So in electrostatics, at least when we've been talking about electric fields, in electrostatics, we can say that the electric field, there's a couple properties here which turn out to be equivalent. It can be written as minus the gradient on a scalar function called the electric potential. Because V is a function, and we assume it's a well-defined function, then turns out that means that the integral of the electric field around any closed path, so it has to be a closed path, must be 0. And this also means that the electric field is conservative. Is a conservative vector field. If any of these things are broken or not true, then all of them are broken. So they're all one-to-one. It all means the same thing. So in fact, for today, to really emphasize this, I'm going to go ahead and write a C here and a C here. I'm going to try to really emphasize the role that this assumption about the conservative nature plays, because we're going to find out that it's not always true. Okay, so that was electrostatics. That's what we had. All right, so let's think about what that means. And in the back of my mind here, I want to think about, so I'll go ahead and draw it here. I'm imagining a situation where I have a battery hooked up to a resistor. Okay, so in the back of my mind, that's the situation I've got in my mind. Okay, so just remember that. So, if you had some sort of a loop of current flow or something like that, and you're running it in steady state, then basically as a bit of charge, you pick a point, you'd have some charge leaving, some charge entering, but you'd want that little point to be steady. So it's kind of like in control volumes in thermodynamics, for those of you who had that with me. So what we would need to do to make sure that happens would be that, you pick a little segment here, a little place on the circuit, you have some charges leaving, some charges entering, and you'd want then the accumulation of energy changes for the charges that leave and go around and come back to kind of zero out, so that over time, what's happening at each place along the circuit is steady. All right. So to keep this in steady state, we need the energy gains and losses around the circuit to add to 0 for each charge which follows that circuit. All right. So what are the sorts of energy changes that you could have? We have a battery, so you could have types of energy change. So you could have batteries, you could have a generator, you could have a solar cell, you could have, well, and then we could also have places in here where there's an electric field. You know, we all know there's going to be a current flow. What makes that current flow? Well, it's the electric field pushing the charges along. So then you could also have energy changes caused by moving in the presence of a, and in this case, I'm going to focus on conservative electric field. So you could have motion in presence of conservative electric field. And there could potentially be other things going on, but I'm just giving you the important ones. So, for example, this would be relevant inside a resistor or inside a capacitor, right? Because in those places you have electric fields in those two situations. All right. So, very good. So basically, we're going to split out two types of energy changes. We're going to have the ones due to the conservative electric field, and we're going to have all the rest. And these, so the way we will handle, well, for the conservative electric field, we'll talk about the energy per charge. So we say delta E over Q, which is going to be the electric potential. And for these, you can think of it as, if you want, you can think of it as the work done on each bit of charge by, the rest of the stuff. So sometimes people will write the work done by the stuff divided by the charge. And the name for that amount of energy per charge is the EMF, written with a script E. It stands for electromotive force, but that's just a misnomer. There is no force there. It's really an energy concept, not a force concept. Okay, so calling it electromotive force is a historical accident or mistake. But the EMF term sticks, but I prefer to write script E anyway because I'm lazy. So, all right. So the EMFs are going to come from things like batteries or solar cells or generators, any non-conservative electric field situation. So the conservative electric field is going to be relevant in the presence of a capacitor or in the presence of a resistor, for example, because you have a current flow there. All right, so those are kind of big picture differences between electric potential and EMF. What about change in voltage? or well, so these both have both the change of potential and the EMF have units of volts. And when I talk about voltage or change in voltage, I'm really just talking about either of these, either the change in electric potential or the EMF, whatever is appropriate. That's what I'm going to talk about. I should have said that that was delta V up there. Apologize. Okay, so let's see how this plays out here. Let's go back to our kind of simple circuit here. Okay, so what's going on in this thing? I have, through the magic of chemistry, some amount of energy. And if a charge were to wander from the minus side to the plus side, there would be a gain of energy as it crosses the battery. That energy change due to chemistry is not well described via a conservative electric field. In fact, it's best described as an EMF. So we're going to have an EMF at the battery. And then we know there's going to be a current flow. And we have a resistance here. And we know, well, why was there a current flow? Well, there had to be an electric field pushing it along. So there's an electric field pushing, and the electric field goes from high voltage to low voltage, or from high potential to low potential. And we know then that the charge that passes through the resistor is losing energy. Okay, so we're going to have, at the resistor, we're going to have a change in energy per charge of delta V. Kirchhoff's loop rule I apologize, it's terrible, is simply the assertion that if you add up all the changes in energy, and since the circuit's supposed to be in steady state, that this is going to be zero. And so that just means we're going to assert that zero equals the EMF of the battery plus delta V for the resistor. And we can rewrite that as say EMF of the battery equals, well, using Ohm's law, I know, well, first of all, I know that if you follow the path of positive current, that the actual voltage is going to drop as you cross the resistor, and the magnitude is IR, and so I'm going to say this is minus, moving it to the, because of moving it across the equal sign, and then it's a drop, delta V is negative, so I get a minus the amount I times R, where I is the positive amount. And therefore I get that the battery's EMF equals IR. Okay, so just to recast this, we have change of potential due to the conservative electric field. We have an EMF, which is basically any other energy that could be given to the charge as it moves around and from point A to point B. And this is going to be due to the non-conservative stuff in the problem, non-conservative electric field or other stuff. Okay. Let's do another example that maybe will clarify things a little bit. So let's imagine you have a battery, and we're going to talk about a real battery, and it's sitting on the shelf. Now, so as terminals, we'll call them A and B. Now, a real battery, so that what's going on inside a battery? Well, you have chemistry, so we'll call that chemagic. We have chemagic happening inside the battery, which is really just code word for all sorts of things like thermodynamics and whatever. And then on top of that, I suppose mostly thermodynamics. On top of that, if we were to hook this up to a circuit, so you can imagine that there's some other thing sitting here, and the name for this other thing is going to be called rest of the universe. Right? You can imagine this is just a really crappy circuit, and there's no wire there. It's just the air. Okay, so the rest of the universe is what's sitting on the other side. And okay, so if a charge were to start to flow, it would, well, first of all, because there's a charge flow, there would have to be electric fields, and we know that there's going to be some resistance. And so the way we handle real batteries is we kind of model them up as some sort of internal resistance. So here's a real battery. Okay, now when it's exposed to the air, there is no real current involved. So, and if there's no current involved, if there's no real current flow, then the change in potential across the resistor is zero, in which case the difference in potential energy per charge between each of the two terminals is simply going to be the EMF is just going to be the chem magic. So that's just going to be the EMF of the battery. So chem magic is the EMF of the battery. I should have said that. All right, so if there's no current, then the energy or the work, so it's kind of the work in going from A to B before you actually do any work. Or you can imagine it would be the work for an infinitesimal amount of charge moving along from A to B. I don't know. Would equal just the EMF of the battery. On the other hand, if now the rest of the universe involves wires and stuff where there is an appreciable current flow, then the work in going from A to B so with current flow, so I is not zero, then the work per charge or the energy change in a charge and going from point A to point B would equal, well, the chemistry's there. Chemagic never dies, so that's going to be the EMF of the battery, plus then you have the change in potential across the internal resistor. Okay, and sometimes people would write that as EMF or battery plus, sorry, not plus, it'd be minus I times R internal. Okay, and so the idea is the EMF would be the magic of chemistry. That's that's the potential energy, or sorry, that's the energy available per charge as you cross the battery before you make it actually do anything. That's kind of the most you could ever get out of it. But in reality, you kind of have to work against the structure of the battery. And so there's going to be some resistance. The body of the battery is going to cause there to be some energy to be consumed and therefore not available. So if you were to measure the voltage from across the terminals, you would get a different answer with or without a current. All right, so this is for batteries, generators, solar cells, and resistors and capacitors. This is the story. And hopefully it explains the connection between potential difference and EMF. And we talk about both of them, all of them, as changes in voltage because they all have units of volts. And they all mix in Kirchhoff's second law. So what I said was that when there was a conservative electric field, delta V equaled minus the integral of the conservative electric field, ds. This is a line integral. And I also said that, so this is the same as saying that E conservative is minus the gradient on V, which is the same as saying that the line integral of E conservative around a closed loop dot ds equals 0. Those are all equivalent statements. You know, I've tried to highlight here in this video the conservative label and the conservative nature of things, and that also then says that if, for example, if the line integral of E dot ds is not 0, then we can no longer say that the electric field is minus the gradient of V. So this would be a non-conservative electric field. So I'm going to label that with an NC for non-conservative. Sorry, there should have been not equal to change of potential. It turns out, this is something called a Helmholtz decomposition, but it turns out you can split an arbitrary electric field. Oh, before I move on to that, what would such an electric field look like? Something where the line integral around some sort of a closed path is not 0. Well, we've already seen such vector fields. These are kind of like magnetic fields. So this would require electric fields to form, or the electric field lines to form closed loops. All right, so these would be electric fields which don't come from charges. So the non-conservative part would be the electric field which is not directly sourced by it's not directly sourced by charges. Because we've already seen if you have charges, then you're going to get field lines which radiate out, not in circular fashions. They radiate outwards, and you would get 0 line integrals. 0 when you integrate all the way around. So this other type of electric field would form, you know, things like a closed loop of electric field. In fact, in general, an electric field may be expressed as the sum of 2 parts, a conservative portion and a non-conservative portion. So we can say the electric field is the electric field conservative plus the non-conservative part. This part may be written as a gradient on a potential. This part is not the gradient on a potential. of any type. In fact, this non-conservative part may be expressed in terms of a time derivative on some auxiliary quantity. In fact, so then I would say the non-conservative part is written as a time derivative. It's actually a partial derivative of some other vector quantity. Sometimes this is called a vector potential. It is beyond what we will need in physics, or in physics 2, in this first course on electricity and magnetism. If you take a more advanced course, this is what you would have. And I guess I will state in passing, if you're in such a course, notice we have not yet described the magnetic field in terms of a potential. It turns out that the magnetic field is written as a curl on A. So these are both more advanced. And but in a more advanced course, you would describe everything in terms of a scalar potential V and a vector potential A, and various time and space derivatives on the two would give rise to both electric and magnetic fields. Okay, in these situations, because for the non-conservative portion of the electric field, or more generally, we don't use a scalar potential only. And if we want to talk about the energy changes due to a non-conservative electric field, we would group that with the battery and generator and other components of the circuit, and describe those energy changes with an EMF. So energy changes due to a non-conservative electric field are grouped with the battery, generator, etc., as an EMF. Right? So the part, you can't use a potential concept because there is no potential function associated with the non-conservative electric field. Instead, you have to just talk about the work per unit charge, the EMF. Hopefully that clarifies the difference between voltage, electric potential, and EMF. They all come together in the form of circuits, but they all have different definitions and kind of different regimes of applicability. All right. See you next time.